So we have now come to the final segment in our lecture, and in this final segment we're going to talk about some probability distributions. Let's first start with a very simple experiment called the Bernoulli trial. It's a simple experiment in which there are exactly two outcomes, and there are many such experiments that you can think of, the classic example being that of tossing a coin. In the context of Bernoulli trials, we normally talk about one of the outcomes as being a success and the other one being a failure. And this Bernoulli trials are often used to model such success-failure situations. And the normal notation is that the probability of success is denoted P, and the probability of failure is denoted 1 minus P. Along with this Bernoulli trial, we can also associate a Bernoulli random variable. Let's call that X for now. X will take the value 1 typically if the outcome is a success, and 0 otherwise. And now the question is, what is the expectation of X? Well, there are two values that X can take. X can either take the value 1 or it can take the value 0. And each of these outcomes has to be weighted by their respective probabilities. And so the 1 occurs with probability P because P is the success probability, and the 0 occurs with probability 1 minus P. And therefore we can work it out to show that the expectation of X is P. So now that we have a handle on Bernoulli trials, Bernoulli random variables, and the expectation of such Bernoulli random variables, let's move on to the binomial distribution. In the binomial distribution, we have n Bernoulli trials. Each with success probability P. And here our random variable X denotes the number of successes that we see in those n Bernoulli trials. Such a random variable is said to follow the binomial distributions. It basically gives you the number of successes. So what is the probability that this random variable X is equal to J? Well, what does that mean for X to equal J? There have been n trials, n Bernoulli trials. Out of them, J trials have come out successfully. The rest have all been failures. So there have been J successes, and the rest have all been failures. Okay. But there's nothing to say that these are the particular J trials that should be a success. Out of these n trials, some J trials have been successes. And how many ways can you actually choose J locations within the n trials? That's n choose J. And now that you've specified that these are the success locations, we have to work out the probability. So this location will be a success with probability P, 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 P. So that all of them together would be P raised to the J. And all the other locations will have to be failures. So all of them will have to occur with probability 1 minus P, 1 minus P, 1 minus P, and 1 minus P. So that's 1 minus P raised to the power n minus J, where since there are n locations, J have been success, n minus J is the number of failures, and that's what you have over there. And this is the probability of X taking a particular value J. Now, we can use this to compute the expectation of x, but that's going to be very complicated. But this is where the linearity of expectation comes in very handy. So in order to apply the linearity of expectation, we're going to assign a random variable to each Bernoulli trial. These are sometimes called indicator random variables because they indicate whether a particular Bernoulli trial was a success or a failure. So x1 will be a 1 if the first Bernoulli trial came out a success, otherwise it would be a 0, and so on. And so it's very easy to see that our binomial random variable x is simply the summation over all I ranging from 1 to n of xi's. Okay, so now we can easily apply the linearity of expectation. So what we want to understand is expectation of x. And that's therefore going to be nothing but the expectation of the summation over all I xi. Well, that's just basically obtained by saying, applying expectation to both sides. That's what we get. And now we apply the linearity of expectations. And so the expectation goes inside and summation comes outside, and you get summation over I, expectation of the individual xi's. But we already know that this expectation of an individual xi is nothing but p. That's what we have over here. And we're again summing it up over n different values of I, and each case the p-value is common, so the total therefore is n times p, which is the expectation of the random variable x. So the third distribution we're going to see now is called the geometric distribution. Here again, Bernoulli trials play a part in the following manner. So consider repeating the same Bernoulli trial several times though, until we get the first success. Okay, the number of trials that we need to perform is let's say is denoted by x, and this x is said to follow the geometric distribution. So let's look at what is the probability that x will take on a particular value, say n. Okay, what does this mean? This means that the first n minus 1 trials were all failures, because had any one of them been a success, then the experiment would have stopped. So the first n minus 1 trials were all failures, and the nth trial was a success. So that's why we have n minus 1 failures and the nth occurrence, nth trial is a success. With a little bit of work, which we will skip for now, we can show that the expectation of x is equal to 1 over p. This particular distribution is very useful in the analysis of in the context of randomized algorithms. And let's suppose we have a randomized algorithm to solve a particular problem, and this randomized algorithm succeeds with some probability p, but it could also fail with some probability 1 minus p. In fact, we saw such a randomized algorithm in the context of Kargar's min-cut algorithm. The algorithm would succeed with probability p equals 1 over n choose 2. Okay, and with probability 1 minus p, it would fail. So the question is, how many times on expectation would we have to repeat the algorithm before it finally succeeds? Well, that's nothing but 1 over p. So in that case, if x equal to 1 over p would be n choose 2. So if we repeat n choose 2 times on expectation, we would see a success. Okay. So you can see how this particular distribution can come in quite handy. And now we will end with the last thing that we're going to see now is the coupon collectors problem, which is a very interesting setting. So we have n coupons, and you can think of these n coupons as being toys that are kept inside of one of those Kinder Joy candies that children buy all the time. Each time you buy a toy, buy a candy, the Kinder Joy chocolate, you get a toy with it. And so so a child is naturally interested in collecting all the toys that are available in this that he or she could possibly get. And each time the child buys the chocolate, it opens it up, and only then can see whether the toy is something that it's already seen before or whether it's a new toy. And the question asked in this coupon collectors problem is, how many chocolates do you need to buy before the child gets to collect all the n different toys that are kept inside these chocolate casings? So let's look at this problem a bit more carefully. So we have n coupons. A trial is the act of picking up a coupon with replacement. So it's like buying a chocolate, and there's so many chocolates that buying one chocolate doesn't really affect the proportionalities of. So for simplicity, we just assume that it's these chocolates or these toys are drawn with replacement. So when you so these coupons are you look at the coupon, and then you see whether it's already it's a coupon that you've already seen before. If you've seen it before, well, that's a wasted trial. If you've never seen it before, well, that means you've seen a new coupon. You put the coupon back, and then you again randomly pick one more, and so on. And so here the random variable x is defined as the number of trials required to see all the n coupons. Okay, so this is called the coupon collectors problem. And what is this expectation of this random variable? Well, again, we're going to use linearity of expectation, and for this we again have to sort of decompose the random variable x into component xi's in the appropriate way. And here's how we're going to do it. Xi is going to be the random variable that denotes the number of trials when I minus 1 distinct coupons have been seen so far. Okay, what type of distribution is Xi? Well, if you've seen I minus 1 coupons so far, well, so you pick a coupon. If it's a new coupon that you've never seen before, it's a success, and you're done. Xi is already that particular phase is already over. But if it's a coupon that you've already seen before, then that's a wasted trial. You have to repeat again. So if you think about it, this is nothing but the geometric distribution. Okay. And here the probability of success, PI, is the probability of seeing a new coupon in a trial after having seen I minus 1 distinct coupons. Okay, And so what is this PI? Well, let's first look at this. This is the probability that you will actually see a coupon that you've already seen before. Okay, there are I minus 1 coupons that you've already seen before, and there are a total of n coupons. So this is the probability of seeing a coupon that you've already seen before, and 1 minus of that quantity is the probability that you're going to see a new coupon. So that's PI. And it works out to be n minus I plus 1 divided by n. And since xi is following the geometric distribution, E of xi is 1 by pi, which is equal to n divided by n minus I plus 1. And so now we can apply the linearity of expectation. E of x is equal to E of the summation over all I xi. And then you apply linearity of expectation, you get that, you apply the formula for E of xi that we've seen here, and so you get this n can be taken out of the summation. You get a summation over I 1 by n minus I plus 1. Just rearranging the summation terms, you get summation over I 1 over I, and this is nothing but the nth harmonic number. So you get n times hn. This is the nth harmonic number, and we know that that is this hn is going to be roughly log n. So this quantity is theta of n times log n.